Hello everyone. I am Masaki Yoshioka. I'm from Osaka University. Today, I'd like to talk about information geometry for a kind of non-regular statistical model. Here is my outline. First, I introduce a non-regular statistical model called as one-sided truncated exponential family. This one. After that, I'll give a geometric structure for that statistical model. Okay, let us see the non-regular statistical model in information geometry. Information geometry has been revealed that the deep relationship between statistical model, statistical theory, and the geometric structure. However, the conventional information geometry focused on only regular statistical model, especially the exponential family. Then, some non-regular statistical models are out of focus. Although these models could be practical. This model, one-sided truncated exponential family, is such a non-regular statistical model. Before the explanation of this model, let us review the regularity conditions and regular statistical model. Okay, suppose consider a statistical model P with coordinates theta. Now, this small p denotes a density function. And when this model satisfies these conditions, this model is said to be regular. In this presentation, please focus on the first and the second conditions. The first condition requires that the support of the density function P is independent of the parameter theta. And the second condition, the partial differentiation respect to theta and the integration on sample space X must be interchangeable. These conditions are very important for information geometric theory. However, our model of interest does not satisfy these conditions. Okay, I'd like to introduce one-sided truncated exponential family, shortly OTF. OTF is a statistical model with two kinds of parameters, n-dimensional natural parameter theta and one-dimensional truncation parameter gamma. The density function is similar to an exponential family, but the support of the density truncated by a truncation parameter gamma. For example, the Pareto models and truncated normal distributions are included in this model. Please look at this graph. As the truncation parameter gamma larger, the support of the density shifts to the right. Then the support of the density depends on truncation parameter gamma, and this model does not satisfy regularity conditions. Next, let us see the statistical properties. Suppose theta hat and gamma hat are maximum likelihood estimators from n samples. In this case, root n times theta hat minus theta denote a normal distribution in rho, just like regular cases. However, n times gamma hat minus gamma converges to exponential distribution. This result is different from regular cases. then the behavior of parameter gamma is some special. Then I'll give a geometric view of this model, OTF. OTF is a n plus 1 dimensional manifold with coordinates theta and gamma. Now, when a truncation parameter gamma is fixed, we obtain a n-dimensional exponential family, written as E gamma. Note that this family E gamma is a regular statistical model. Vice versa, when we fix theta, we obtain a one-dimensional non-regular family. Then OTF consists of these two families. For information geometry for OTF, first we should discuss the suitable geometric structure. In regular models, Fisher metrics and alpha connections are very important. Thus, some previous researches for Pareto models follow the formal definitions. However, the statistical theory of OTF is different from regular cases. Then, we don't know these geometric structures are related to statistical theory of OTF. Now, let us reconsider the geometric structure of OTF. In this presentation, I'll give a Riemannian metric and affine connections for OTF. First, let us discuss the Riemannian metric defined from asymptotic property of OTF. Here is my definition of Riemannian metric on OTF. Now, index I and J denotes the natural parameter theta. The part of natural parameter corresponds to the Fisher metric, and the tangent vector in direction theta I and in direction gamma are orthogonal. This Riemannian metric is related to the maximum likelihood estimators. Consider root n times theta hat and n times gamma hat. In this case, the first term of asymptotic variance is written as the inverse matrix of this Riemannian metric. This result is similar to the Fisher metric in regular cases. After Riemannian metric, I'd like to talk about affine connections. Here, recall that the some model E gamma is an exponential family. For the definition of affine connections, I focus on the fact that alpha connections on exponential family are always equiaffine. Thus, I have an idea that to construct equiaffine connections on OTF as an extension of alpha connections in exponential family. Now, let us review the definition of equiaffine connections. An affine connection delta is equiaffine if there exists a volume element omega such that the covariance derivative is always zero. Such a volume element called as parallel. In information geometry, alpha connection in exponential family is equiaffine for all alpha values. equifying connections are related to Bayesian statistics. In Bayesian statistics, there is a deep problem that how to set prior distribution when we don't have any information for parameter spaces. For this problem, from the geometrical viewpoint, this prior distribution is regarded as a volume element. Then, if alpha connection is equifying, there exists a parallel volume element. Parallel volume element is regarded as a uniform volume element, and it is natural for the non-informative cases. Thus, we obtain a prior distribution from this parallel volume element, called as alpha parallel priors. Okay, now let us return to constructing equifying connections on an OTF. Here I propose two families of affine connections. First, alpha connections is a family of affine connections defined by this formula. This formula is used in alpha connections of regular models. Second, beta connections is a family of affine connections with parameter beta, defined by one connection above and Levi-Civita connection. These two families are same on regular models. Then, both of them are extension of regular alpha connections. For these two families, I checked the existence of alpha parallel priors. Then, this is my theorem. Alpha connection on an OTF is equifying when alpha equals 1. Then, one parallel prior exists, and the explicit form of one parallel prior is minus partial gamma psi. This value is always positive. However, this result is different from the case of exponential family. Exponential family has alpha parallel priors for all alpha values. On the other hand, beta connection in OTF is always equifying, and beta parallel priors exist for all beta values. This result is similar to the case of the exponential family. Thus, we have constructed a family of equifying connections on an OTF. Okay. In addition, let us see the relationship with the reference prior. Reference prior is a famous non-informative prior in Bayesian statistics, but I omit the details. By Gossal's results, a kind of reference prior in an OTF is written as this form. Here, theta are nuisance parameters and gamma is a parameter of interest. Thus, Gossal's reference prior corresponds to our one parallel prior. Then we give a geometric meaning for this reference prior. Finally, I'd like to summarize my presentation. First, I introduce a non-regular statistical model, OTF. Then, I defined a Riemannian metric for OTF based on the asymptotic property. After that, I discussed about affine connections for OTF and constructed a family of equifying connections, beta connections, as an extension of regular alpha connections. the end of my presentation, I propose two open problems. First problem is about the relationship with statistical theory. In regular models, alpha connections are related to the higher order asymptotic theory. How about our beta connections? Second, we should consider a potential of other geometric structures. Since OTF has since statistical property of OTF is different from regular cases, then non-Riemannian structure could be better. Here are the references. Thanks for the listening.
Déjà, merci pour ces brillants exposés. Je vais te poser ma question en français. Ah. Ok. Bien. Je voulais demander comment tu vois l'existence de la bêta connexion sur la variété. L'existence.
The question is existence of beta connections on
Manifold.
Okay. Sorry. You mean first confirm the existence of this connection, right? But in this case, Levi-Chavita connections are already exist, but this log likelihood function is log likelihood function cannot be differentiable by parameter gamma at x equal gamma. Then I ignore the I ignore this term at a point. But we can define this beta connection formally. Okay.
It is a deformation of Riemannian connection. It is deformation of Levi-Civita connection.
Sorry. This Levi-Civita connection is defined by the this Riemannian metric.
Okay. Merci.
Thank you.